Did you have that G has a relative max at -2? If you did, awesome. But the point is earned by telling me that G prime or F changes signs from positive to negative. So even if you had that x equals -2, the only way to earn your points is to either label it as G prime or F and tell me that it changes from positive to negative. For part B on that FRQ review page, it says the graph of G is concave up, and you could give your interval like this, where it's -1 to 1. You could also give your interval as a bracket notation. So you could have used parentheses to give your interval notation, and you could have used that's probably about the only other notation you could use. And then the reason we did this FRQ when we did is because we recently learned L'Hopital, and in part C, that was L'Hopital's rule. So in order to find the limit of that function, we had to realize that that function was the indeterminate form. And then once you identified that it was the indeterminate form, you were going to apply L'Hopital's to find your limit. And then yesterday, I kind of went over it in class, and I can send what I wrote on my whiteboard for part D. But essentially for part D, you wanted to take the integral of h of x and first break it down into two integrals. So I break it down into the integral of 4, and I break it down into the integral of 3f 2x plus 1. And the reason I did that is because the integral from -2 to 1 of 4 is going to give me a rectangular area under my curve. And then over here, I'm going to use u substitution to get rid of the complicated part, change it to u, change it to du. Upon doing that, I have to actually then change my bounds as well. And then again, like I said, this is just the rectangular area with base 3 and height 4, so you're adding 12 to that area. And then when you change your bounds from -3 to 3, that actually gives you the area under the entire curve, so you add the pieces that are above and you subtract the pieces that are below. So we're going to add the pieces above and subtract the pieces from down below. Are there any questions for me on that FRQ review for your response? Anything on that answer key you didn't understand? We're going to actually do the other FRQ together. And then I just sent it out. Well, I was actually waiting for the due date of, 8:30 or whatever. So I just sent out the U sub answers on Teams, but I'm going to pull those up so you guys can look at those. So essentially, this is the U sub answers to the other part of the worksheet. So you can take a minute and Okay. And then on page 2, and number 8. Did we do okay? I know USub gave us some difficulties those first few days, so hopefully it's really starting to click. You're seeing the difference between plus C's and definites, where you're going to get a numerical answer. You're starting to understand which values should be your U and which values should not. Okay. And then the last handout I want to go over was the other free response handout that you had in that packet. So we're going to go over that one last free response question, which was at the end of this packet, and it involved the graphs with F, F, but it represented G, G prime, etc. So the warm-up says a particle moves along a straight line. Its velocity is inversely proportional. So an inverse proportional velocity. So inverse, you're thinking like multiplicative, reciprocal. You're thinking, along those lines. So its velocity is inversely proportional to the square of the distance. So square of the distance. So I'm looking for S squared. So inversely proportional to the square of the distance. I'm looking for S squared. Which describes this equation? Well, immediately I can get rid of letter C. There's no S. I can also get rid of letter A. There's no S. And then we're talking about velocity. So it doesn't mention dt, but we're talking about velocity in terms of time. So both dv dt here and here are similar. The difference is this is the derivative of velocity with respect to time. This is the derivative of velocity with respect to distance and talking about time. So our correct answer is B. So like I said, we're picking up with slope fields. We're looking at slope fields today. We're going to talk about slope fields and their relationships. So we also are going to talk about differential equations. A differential equation is an equation in terms of x and y. So think implicit. Implicit involved x and y. But a differential is going to involve derivatives of y as well. A solution to a differential equation is a function that satisfies the differential equation when the function and its derivative are substituted in. So we're going to be substituting again. So chapter 6 is a lot of substituting. A solution to a differential equation could be one function or a set of functions. So one function is going to be an initial condition where you find a value. A general is going to be with your plus C. And then just discussing and reviewing our vocab, a definite integral is an integral with an upper and lower bound. So a definite integral is an integral with an upper and lower bound. So that's like a to b of f of x dx. And then an indefinite integral is the set of all antiderivatives of a function f of x with respect to x, and it would look like f of x dx. And we know that its antiderivative is that capital F of x, and its answer is always going to have a plus c. These are examples of differential equations. This is what they will look like on an AP exam. They're going to have derivatives mixed with derivatives mixed with non-derivatives. So like y double prime, y prime, y. Second derivative of y with respect to x plus 2 derivative of y with respect to x equals 3y. Okay, and then I just have that recall for you. So if you recall, direct variation occurs when a situation gives rise to a linear function, f of x equals kx or y. So again, we have this idea that these functions are going to essentially have some sort of inverse proportional properties that we're going to see reflected among them. Puppy gains weight at a rate approximately inversely proportional to its age. Write an equation that describes this relationship. So we're coming up with an equation where W represents weight, T is time. So the rate of change, anytime we talk rate, we talk derivative. So dW dt is equal to, K represents our proportion. So it's just generic K. That's the constant of proportionality with respect to time. And honestly, this should look like a formula we've sort of seen in the past, where K is kind of like distance, D is time, and R is rate. So think about the fact that we said distance equals rate times time. If you rearrange that, it would be rate equals distance over time. So a lot of what we're talking about with differentials is very similar. If you think about a rate is kind of like your derivative. So that's kind of like dr dt equals d over t. dr dt equals d over t. That's what we're looking for in a lot of these problems. Example 2. An IV drip administers medication to a patient's bloodstream at a rate of 3 cubic centimeters per hour. The minute I see cubic, I know I'm talking volume. That's also kind of like my initial condition. At the same time, the patient's organs remove. So when I see remove, I'm thinking negative. If I see proportional, I'm thinking K. So the removing is proportional. So I know I'm going to have a negative and a K, and it's proportional to the current volume. So I need a negative, a K, and a V all to be together. Which equations describe the relationship? So all of them start with dV dt, so that doesn't help me eliminate anything. But now I'm looking for a 3 to be alone. And the reason for that is because this is kind of like your rate in. That's what's being added. This is the rate out, or what's being removed. So this goes back to what we just talked about with rate in, rate out. So the rate in is 3. Well, that's the only one where 3 is alone. So it's A. And then the rate out, well, you can see the negative, you can see the proportion of constant, and you can see the volume. So what we're going to do is extend on that idea. So that's proportions, that's rate in, rate out. That's where we came from. Now we're going to, where can we move to? And we're going to move to differential equations. And differential equations say a function is a solution to a differential if there is a y and dy that satisfy that function. Solving a differential equation involves finding a unique equation that satisfies some initial condition. The order of a differential equation is the order of the highest derivative involved. So sometimes we're going to start with second orders. Sometimes we're going to start with first orders. But all in all, we are going to look at these initial conditions and derivatives to find these solutions. So that very first question says, solve the initial value problem explicitly. So if it's explicit, then you're separating your variables. So the way this problem's currently set up, my variables are not separated. dy and dx are together. So what I'm going to do is rewrite them, kind of like what we've been doing with u substitution. So the dx is with my x. So you can almost see how this looks like that line of u sub. Du equals sine x dx. So we need to get to y. So how do you turn dy into y? How do you go from y prime back to the original? You integrate. So in order to solve an initial value problem, we're going to integrate with separated variables. So the integration of y prime is y. The integration of sine x is negative cosine x. And then plus c, because this is an indefinite integral. But this value here, that y of 0 equals 2, well, that's going to allow me to solve for c. So what that says is y is 2 when x is 0. What is c? Well, the cosine of 0 is 1. So you get 2 equals negative 1 plus c, which means that my c value has to be 3 because 3 minus 1 is 2. So my y value, or my y equation, is negative cosine x plus 3. So if you see an equation or a direction that says separate the variables or solve by differential equations, that's what this is. These are differential equations. You're really just finding the derivative or the antiderivative the exact same way we've been finding it, but now the directions are changing a little bit in the fact that we don't have y prime over on the left, you have dy. And you start with dy dx together. So you're kind of anti-deriving both the y and the x's now in a different formation. So this time we switched it up. We have dx and dt. So the rules don't change. We want to separate the variables. So you have dx on the right, and then you have 1 over t, and you can distribute the dt to each term. You can write it at the end. It doesn't matter, so that's it distributed. You can also write it so you have dx equals 1 over t minus 1 over t squared plus 6, and put the dt at the end. But we're going to take the antiderivative, or the integral of both sides. So the integral of dx, that's like 1 dx, right? So the antiderivative of 1 is the variable that you're taking the integral with respect to. So the variable is being integrated with respect to x. So this is x. 1 over t is really like t to the negative 1. So the rule is to add 1 to our exponent. So that's where we get the special case, or ln. So 1 over t's antiderivative is ln, absolute value of t. T to the negative 2, well, that one you can add 1 to it. So you get t to the negative 1 over negative 1, which is really like minus 1 over t, plus 6t, because you add that variable's constant back, and then plus c. And then we're going to use our initial conditions and solve for c. Yeah. Yes. Thank you. Thank you. Thank you. So 1 and 6 makes 7. The natural log of 1 is 0. So you get 0 equals 7 plus c, which means that c is equal to negative 7, which means that my equation is x equals ln absolute value t plus 1 over t plus 6t minus 7. One of the things or areas I noticed with integration we have issues with is discontinuity. So what I want to do with you now is look at an initial value problem that involves discontinuity, because we know that the secant function isn't continuous. It's kind of like our function that looks like the sad man. So you have those areas in which you have vertical asymptotes. So we just have to be cautious when we look at this graph to make sure that we are incorporating or taking into account those vertical asymptotes when we get our antiderivatives. So it says find the particular solution. So once again, in order to find, if you see the word particular solution, you're thinking separation of variables. So we're going to put dy on the left. We're going to take 2x minus secant squared x.
Good morning. At this time, any staff members want to come down to the library for the Aquos board training. We're going to start in a couple minutes, so see you in a bit.
I am going to that, but they know I'm coming late because they know I care about you guys so much. So we are going to take the antiderivative of this. So the antiderivative of dy is y, because again, that's like 1 dy. So you get y. The antiderivative of 2x is 2x squared over 2, so you cross out your 2's. And then The antiderivative of secant squared x is tan x, and that's one of our rules. So if you think about the derivative of tangent, it's secant squared. So the antiderivative of secant squared is tan. So that becomes minus tan x plus c. And because 0 is on the domain of both secant and tangent, we can plug in our 3 and 0 and solve for c. The tangent of 0 is 0 because sine of 0 is 0. So you get c equals 3. And we have y equals x squared minus tan x plus 3. So discontinuity, again, does not affect our function unless the function is being found at a point of discontinuity. So I just want to stress that you can integrate a function that's discontinuous if it's continuous at that particular point. Okay. We also solve initial value problems involving fundamental theorem of Calc. So fundamental theorem of Calc has been a big topic for us over the past couple weeks. It's the fundamental theorem. It's going to be everywhere. You have calculus problems pretty much when you get down to your free response questions, because it's really saying, do you understand how calculus works both in the forwards and backwards motion? So do you understand the relationship between derivatives and antiderivatives? And hopefully you do. Hopefully you understand that like the derivative of an integral cancel each other because they're inverse operations. And that you understand that the integral of a function is equal to the function's antiderivative. So if you integrate f prime, then you're going to get f. And if you integrate f prime from a to b, then you're going to get the area under the curve of f of b minus f of a. And that is the most basic definition of an integral. So in the case of this problem, we're going to separate my u's and my x's. And you have two choices now. You could do u substitution, or you could get rid of your square root. But since we need practice with u sub, let's turn underneath that radical into our u. So u would be equal to 2 plus the cosine of x. Du would be equal to the derivative of that. Oh, well, that's okay. And then what do we notice happens when I try to do that? What am I missing? So we're going to have to manipulate this a little differently now. If you want to solve a problem missing parts of your problem and fundamental theorem and u sub doesn't work, then, and honestly, I think this came from a multiple choice question, which means it would be easier for you. Go back to your idea of separation of variables, because that's what we're now talking about. And we have our dx's and our u's, and we have our initial conditions. So how can I incorporate an initial condition? Well, fundamental theorem. The fundamental theorem of calculus says that if you integrate both sides, you have u, and then we have this integral that we can't do anything with because we can't use sub because there's no sign. And we don't know. So the idea is, though, this is an indefinite integral. So over here, if you antiderive the left side but not the right side, your constant of integration is over here. But we don't like the way that looks, so we move our constant of integration to over here. So you took the integral of the left, and you at least got this in terms of u. And we know that u is -3 when x is 0. That says my answer is going to contain an integral. So if you think about the fundamental theorem of Calc, it says that f of b equals the integral from x to 0, or you could do 0 to x of f of t dt plus f of a. So transforming this equation into that idea, f of a is kind of like that given point up there. Instead of 0, we're going to use my initial condition, which in this case just happens to be 0. So this is kind of like saying f of b equals, which f of b is our u, the integral, initial condition, and its input. This is unsolvable in Calc 1, which is why our answer has to contain a definite integral. And a definite integral had to have bounds. So when we're solving our initial value problems, we're really applying the fundamental theorem of Calc. And that's sort of the idea behind that concept. How does this relate to where we've been? And the relationship is that it is an application of what we were doing. So we can separate those variables, which is what we've been doing up to this point. And this is some ways that it will look or appear. So you're going to see a problem that looks like this. It's not going to have y prime in the way we were seeing it in the past. So in the past, we just said dy dx equals 2x over y. So that's another way. These two are the same thing. So this is an extension of what we've been doing, except for now, what you'll notice is I have two variables. I have y and x. So now this looks like implicit. And what you're going to do is essentially cross multiply. So the y's are together and the x's are together. And again, take your antiderivative. We only put plus c on one side. You only add plus c on one side. And again, we like to have our y values solved for. So we're going to multiply both sides by 2 and take our square root. And that plus c, it just like sort of tags along. It doesn't need to be under your square root. It doesn't need the 2. It's going to encompass any or all parts of that. Here are a couple more examples. So your original, that's like our implicit back in the day, rewritten as separated. So this looks like our implicit. So you'd subtract your x squared, multiply, well, you don't even have to multiply by 1/3, but you could. But then you're definitely going to multiply by dx. So your dx is with your x and your dy is with your y. So the only way to take an integral is to have what we call the constant of integration. So in your integral formula, you'll notice I always stress and write that dx. That's your constant of integration. So if you're going to integrate, you need a dx. I don't care what's over here and what's happening, but you need a dx. And that's why we have to separate our variables, because we need that dx. So let's look at one more example, this time with a cosine. So cross multiply. Take your antiderivative. Sorry, it would be a plus sign. And if you wanted to get the y away from the sign, you would take the inverse sign of both sides. And you'd have sine inverse x to the 4th plus c. But if you were given y's and x's, I would leave it like this and just solve it, because the inverse is maybe going to be more difficult for you. The only reason it would be easier is if your answer was given as like a radical, but if it is given as a radian, I would keep it here. So again, these are interchangeable. They mean the same, and they'll solve the same. So speaking of solving and being given conditions, let's do a differential equation given an initial condition. Now we're given an x and a y. To antiderive this, we want to get the y's on the left and the x's on the right. So we're going to divide both sides by y. We're going to multiply both sides by dx. And you're also going to divide by that x squared plus 4. So that's going to leave you with 1 over y, because I divided by y, dy, equals x over x squared plus 4 dx. Hopefully by now you know that the antiderivative of 1 over a variable with respect to dy is ln. And over on the right, that's a u sub. So you want to make sure, because your initial conditions are given with x and y's, that you get your final answer back to x and y's. And then you're going to plug in those initial condition values. So 9 plus 4 is going to give you 13. Moving this part over, you have minus 1/2 the natural log of 13. If I was going to write my answer in terms of y, I would have to, so I have ln absolute value y equals 1/2 ln x squared plus 4 plus ln absolute value 2 minus 1/2 ln absolute value 13. So we know that our rule is that if you have ln's and they're being added or subtracted, that's really like multiplication or division. So that's like ln absolute value y equals 1/2 ln 2x squared plus 4. And then since it's 1/2 and 1/2, that's really like the square root power. But this is all over 13 because it's division with subtraction. And then we're going to bring that up as my power. And then to get my y alone, you e both sides. And what's nice is in both of these cases, the e's and the ln's cancel. So e and natural log of y and e natural log of all of that cancel. And I get that y is equal to the square root of 2x squared plus 4 all over 13. The last thing I want to show you before your mock exam is a slope field. So a slope field, we're going to actually skip the warm-up page. It's in your textbook if you want to see it. So this page is in your book if you want to see it. I can also send you the answer key to it. But because we're already 45 minutes in, I want to just show you a slope field so that you can actually practice some things on your own. So a slope field is essentially the first differential order. So that blank is slope field. So a slope field is essentially the first differential order. And a slope field is going to look like a series of segments. So if you had dy dx and it's equal to negative x over y, maybe you remember what function gave that derivative. Maybe you don't. A slope field essentially is a series of line segments that represent the slopes. So if your function was dy dx equals negative x over y, you could create a table to represent that slope field. So your table is going to involve the coordinates x, y, and then it's going to involve the slopes of those coordinates. So if you picked the point 1, 1, the slope at 1, 1 is negative 1. So on your slope field at 1, 1, you would draw in a line segment with a slope of negative 1. If you picked 2, 2, your slope would be negative 2 over 2, which is negative 1. So at 2, 2, you draw a line segment with the same slope that you drew at 1, 1. If you picked 2, 0, you get undefined. Well, an undefined slope is a vertical asymptote. So that would be a vertical line. And we know that if we pick any point on this line, the y value is going to be 0. So all of these are going to have vertical asymptotes. If you picked the inverse point, 0, 2, now your slope is 0, which is a horizontal line. And anytime your x value is 0, my slope is 0. And this process could be continued for all of the points. And anytime the numbers are the same, your slope will be negative 1 in this direction. If you did your opposite points, so let's say you pick negative 1, 1, well, now you have negative, negative, so you get a positive, so these would have positive 1 slopes. And the idea is that you could continue to construct a slope field for every point on your graph. And for time purposes, I'm going to just fill this in a little bit, because I actually already know what my slope field is. And if you can follow along slightly to how I'm drawing in those points, maybe you've figured out what this slope field is. If not, let's do what we just did and summarize slope fields, because the summary idea is that a slope field equation can be found by separating the variables. And you get y squared plus x squared equals c. And then that c would represent what family of circle values you get. So if c was equal to 2, that would represent a circle of radius square root 2, because this is the equation of a circle. And if you look at your slope field, hopefully you can sort of see that if you picked a point and you followed it along, you would get a circle. That was a little rough on my end. I couldn't see under my own hand. There you go. So on and so forth. So a slope field represents the slopes of the original. A slope field represents the slopes of the original. So the slopes of a circle are represented in the red, whose equation is represented in red, and then the blue represents the initial equation. So we're going to do more on slope fields on Friday. We're going to go more through all the, textbook assignment from this. I want to give you time to work on that. So what I want you to do is you're going to go to page 327 in your book. And you're going to work on some practice problems that are due on Friday. I know tomorrow's our mock exam. But again, I really want you to do well on your mock exam to give you an idea of what we are doing. And there are slope fields and differential questions on there. So getting that extra practice in today is going to really help you. So you're on 327. And we're going to do the odds. So you can check yourself in the back of the book. And we're going to start with number 3. And go to 21. So you're going to do 3 to 21 odd. And then I want you to look, there's a matching area for slope fields. So I want you to be able to kind of look at the matching. So you're going to look at 35 to 40. And then do one slope field on your own. And I apologize, it's actually backwards a step. But I'm going to have you do the slope field for number 31. And tomorrow, before our mock exam, if we have any questions on these, I'll gladly go over them, and then we'll start our mock exam. All right, guys, I'm going to go get down to that training. I'm only like 40 minutes late. But hopefully this is all going to piece together for you. It takes some looking over. Your textbook is actually not a bad resource for this unit. Because it actually explains this stuff fairly well. So that is all.